so that I'll be able to upload some. So, all right. So, mainly we discuss about 3 new number systems to you. So, they are binary, octal, and hexadecimal. Binary number system, we have 2 symbols, 0 and 1. Octal number system, we have 0 to 7. And hexadecimal, we have 0 to 9 along with the letters A to F. Okay. So, in conversions in between number systems, if you want to convert any of these a decimal number into any of these systems, what you have to do is actually, you have to do a similar thing. As an example, if we get this, decimal to binary conversion, we divide it by 2. Okay. So similarly, if you want to convert a decimal to octal number system, what you do is you divide it by 8. And decimal to hexadecimal, what you do is you divide it by 16. Okay. Since this does not have any fractions, we do it by repeated division. However, if there's a fractional part, you have to consider that separately. And then you have to convert that by multiplying by 2. The fraction part need to be treated separately. Okay, so it need to be multiplied by 2 and get the carry and arrange it as this. So this would be the final answer. You have to get 2 parts separately. So the question was 11.375. 375.375 is converted in this way. And for 11, we have to divide it by 2. Okay. So that's the conversion into binary. So if you want to convert it octal, we do the same thing. We divide by 8 and we multiply by 8 here. And if you are asked to convert to hexadecimal, you have to change this, divide by 16 and multiply by 16. So that's how you can convert decimal number into any of these 3 numbering systems. And we talked about octal number system and hexadecimal number system. And then we talked about how we can interchangeably convert in between these numbering systems, octal to binary as an example. So if this is the octal number, what you have to do is you have to get each and every digit and convert it into 3-digit binary equivalent. Okay. So then after that you can write the whole number in binary form. So this is for octal numbers. This is mainly because you know 8 is equal to 2 to the power 3. So we need 3 positions to represent a single octal digit in binary number systems. So if you are asked to convert hexadecimal number to binary number system, what you have to do is, so 16 is equal to 2 to the power 4. So we need 4 positions in binary system to represent a single octal number. So single hexadecimal number. So if there was a hexadecimal digit here, what you have to do is you have to represent this with not 3 numbers, 4 numbers. Okay. Each and every digit needs to be represented with 4 numbers rather than 3. So after that, you can together write the binary or hexadecimal number, collecting all these binary conversions. So that's how if you want to convert octal or hexadecimal number into binary, that's how you have to do it. Okay. So this is the hexadecimal number into binary. You can see we represented with 4 binary digits. And you can do it interchangeably. You can convert this octal to hexadecimal or hexadecimal to octal also using this method. So you can start from the hexadecimal number, and when you are converting to octal number, what you have to do is simply first convert the hexadecimal number into binary number. Okay, for that you need to consider each and every digit and represent each and every digit with its corresponding 4-digit binary number. So then after that, you have to just divide it into 3 blocks starting from this end. Okay, starting from the right hand side end, divide it into 3 blocks. You can see how it is divided into 3 blocks, and then it can be converted into corresponding number, binary number. Okay, so this is represents 0. Sorry, decimal number. This represents 5 in decimal, and this represents 6 in decimal, and this represents 2 in decimal. So when you, after converting it, you are to have got is actually the number in octal form. Okay, so when you are converting it into a octal, so you know with 3 numbers you can represent only up to 7. Okay. So that's why that would not go beyond 7. So the numbers would be would match with the numbering system's digits. And there's a conversion system algorithm if you want to use. It also can be used to convert these numbers. And the binary arithmetic rules we discussed. There are 4 basic rules for addition, subtraction, multiplication, and division. So you know addition. For these 3 cases, it's very simple. What you have to do is actually add them together without considering much detail. However, when you add in 1 with 1, it becomes number 2 in decimal. However, that when represented in binary number system is 1 0. Okay, you have to get keep 1 zeros, 0 in the corresponding position and take 1 into the carry. And in subtraction also, so you can see in subtraction with 0, 0 is simple, and 1 from 1 is simple, and 1 from 0 is simple. 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 0 is 0. However, when you are going to subtract a bigger number from a smaller number like this, what you are doing is actually you have to borrow 1 from the other hand side. So that's simply matching with the procedure we follow in decimal number systems. And in multiplication, I think there's nothing new to know, just you need to multiply them together. And the division is also not very difficult. So you are going to put a value only if when the number you are going to divide with is bigger than the number you divide. Okay. And binary division is as an example discussed. So you can see you don't, you just put 0 values when this number is bigger than this number. Okay, so that's what I told earlier as well. So that's also, I mean, analogous with the way we do it in decimal number system. So in decimal number system also we can put 1 here only if this number we are going to divide is bigger than the divisor. Okay. So you can see the situation where we subtract or not subtract, that is analogous to decimal number systems. There's no problem associated with that. And then negative number is representation. So up to now what we have revised is actually we discussed about 3 computer related numbering systems which are required for a computer scientist. So they are binary number system, octal number system, and hexadecimal number system. And in those number systems, up to now we discussed how we can convert in between these number systems, including decimal number system. And then we discussed how we can do some arithmetic operations with these numbering systems. And after that, we are talking about negative numbers, how we can represent negative numbers in the computer. Okay. So there are several ways of representing negative numbers. Sign multitude representation. sign 1's complement representation and 2's complement representation. In sign magnitude representation, actually there's a single digit which should be used specifically for the representation of the sign. Sign mean negative or positive. Okay. So if it's negative, we will use negative number sign represented by 1. If it's positive number, the sign is represented by 0. So if 1 is there, there's no value represented by 1 rather than the sign. Okay, so that's why we call it sign magnitude. Okay, so if it's 1, it represents a negative number. If it's 0, it represents a positive number. In trying sign 1's complement representation, so how we do it is actually, so it has 2 representations of 0. So we just reverse each bit to get 1's complement. So if this is the number, okay, up to this point, we just reverse it. We put 1 into the places we have 0 here, and 0 into the places we have 1 here. Okay. So the problem there is you have 2 representations of 0, and it is used by some older computers. But 2's complement notation is better than 1's complement representation. So how do you convert a number into 2's complement? So first we write the positive number of the number in binary. So you can see plus 5 is represented by 4 digits in this form. So then we reverse this to get 1's complement. So 1's complement representation of any number is taken by converting each and every bit into its opposite. Okay, opposite means 1 is converted into 0 and 0 is converted into 1. So now we have got the 1's complement. So after getting that, to get the 2's complement number, what we do is we add 1 to the number. Okay, so for this number, what we do is we add 1. So when 1 is added, we will get this number as the added number, which would represent -5. So how can you verify that this represents -5? So I mean, you should know the reverse of, I mean, if you are given the 2's complement number, you should be able to get the corresponding value like this. So how could you get that? I don't know whether I discussed that. Did I discuss how you can convert 2's complement number or 1's complement number back to its decimal value with the sign? Did I? Did I discuss that? Can one of you remember? Okay, so although you can remember or not, can you hear me?
Yes, madam.
Okay. So I will share the white screen and discuss how you can convert this number 1, 1. What's that? 1011, which is the So this is the representation, 2's complement representation of -5. Okay. So what I'm asking you is to convert this. So what you have to write is actually convert this into its corresponding decimal value. So we know that is -5. However, let's see how you can convert that. There are 2 ways you can do. You can do the opposite, you follow. So what we did to convert in this into this form of 5 is actually we wrote 5 in +5 in with 4 digits, and then what we did was we did the we converted each and every bit into its opposite, 0 into 1 or 1 into 0 and then added 1. Okay, so you can do the opposite. You can get 1 out of this. So it would end up with 0, 1, sorry, 1, 1, 0, 1, 0. Okay, and then you can convert this. When you are converting this, so you would get 1, sorry, 1, 0. So what we did was we removed 1 from this corner, and then we converted that into this form. So this would end up giving us 5 as the value. Okay. So this is how we can find out which number we represented. So the other way actually what we can do is -5 is represented here. So the other way you can do this, if you are given, so what we do here is if you are given a 2's complement number, how you can get the value represented by there. Okay. So the first easiest way is to do the opposite. Okay. So you remove 1 and then get the complement, or you can get the opposite of each and every bit, and then convert that into decimal and put the negative sign in the front. So that's the number you have to represent. So the other way you have to do is actually, so get the positional values of each and every number. So for the first one, what's the positional values? 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So the positional value is 2 to the power 3. It is equal to 8. Okay. The positional value is 8. 8 into 1. So for the first one, we put negative value because this is a negative number. And plus, what's the positional value of second one? 4, isn't it? So let me know whether I'm doing a correct thing or wrong thing, okay? Positional value is 2 for the second position. And 1 for the first position. So how much is it all together? -8 plus 0 plus 2 plus 1. 2 plus 1 is 3. 3 negative 8 is 5. -5. So this represents -5. So that's the second way you can convert a number, whose complement number, into its corresponding decimal number. Okay. So this is the second way. What you do normally when you are converting this into whatever decimal number system, we do the normal thing. We get the positional value and multiply it by the corresponding digit. However, for the first digit, since it's a negative number, we put negative value, negative here. So that's the thing we did specifically for this. I mean, rather than doing it in the normal way, converting a binary number into decimal, what we did specifically is putting this negative sign here. You put this negative sign here mainly because in 2's complement numbers, you should know if it represents 1, this also give you the sign. If it's 1, it's negative sign. Okay, you have to remember that. So, so we put negative sign here. If 0 is here, we would not put 0. -9 here in a 2's complement number. So since 1 was there, it implicates that it's a negative number, and the first position also has a value. Okay. Not like in sign magnitude. Sign magnitude, the first position only indicates the sign. It doesn't have a value. So that's it. You can read books and you can have a look at the web There are many nice videos to study about these conversions and negative number representation. It's up to you. Okay, this is University of the School. Okay, so let's. I will then move to the presentation. So that's how we can represent the negative values. So then we talked about arithmetic addition of 2's complement numbers. There's no special processing required. So you have to discard any carry out of the sign at the sign bit. So you can see how these numbers are added, and you can also practice. And subtraction, there are some things you need to consider. So you have to consider a subtraction. You have to convert a subtraction to a addition. So you have done that in your secondary schools also. What you have to do is actually you have to consider these. If you have two numbers as -6, negative or positive 13, what you have to do is actually you can convert it into this form. Okay, so then it's a addition rather than subtraction. So this is -6 is subtracted from -13. Okay, so then it is converted into addition by converting each and every this into a plus sign, which should not affect the meaning of this. So what you have to do is first convert each and every number into its corresponding binary number. And then after that, you can do the addition simply in the same way we did. Okay, so this is the carry out and we are not considering that. So +7 is converted. This can be seen in this number. And here also the same you can study. In unsigned binary representation, you should know the range that's representable. And in signed magnitude representation also the same. So it can represent only from -2 to the power n minus 1 -1 to the power n minus 1 -1. And so the overflow occurs when you can't represent a number within the given width of the register. So assume that you are going to save this in a register in the CPU. So you know in the central processing unit, there are memory storage units which are called registers. So these registers are not, does not have a very long, they are not very long, their capacity is limited mainly, that's mainly because that's purposefully actually they have made it, mainly because the processing unit works very fast. Okay, to tally with that speed, we should have limited memory. Okay, memory units. So those units are called registers. So when you're working with these registers, when you're asking the computer to add numbers or subtract numbers, and after when you are storing the result value, if that result is greater than that register, or if it's, I mean, it's not the only case. Sometimes you can't store that value in the register. Okay, the overflow occurs. So it's a problem with digital computers. So overflow is defined with these conditions. Sum occupies n plus n digits. So you are going to add two numbers with having the maximum length of n. And then after you get the summation or the subtraction, you get a number which has n plus 1 digits. And the last two carry bits are 1, 0 or 1, and we say an overflow occurs. Okay, So that those are the conditions you need to check whether there's an overflow occurred or not in the operation. So this is an example for overflowing. You can see 7 is added to 3. So you can see this is the 2's complement representations of 7. So this is the 2's complement addition of two numbers. So when you add, what you get is actually -6 when you consider. So this is mainly because there's an overflow occur. You can see here, so the carry numbers, okay, carry bit numbers. One is added to 1, 0. So you take 1 to the next position. 1 is added to 1. And with the carry, it's 3. 3 is represented in binary as 1 and 1. So 1 is kept here and the other one is taken to here. 1 and 1 is represented with 0 and 1. So 0 is kept here and 1 is taken into other position. So there you can keep 1 and the carry is 0. So 0, 1 is the condition. Second condition is satisfied, and also this number representation only needs 3 numbers. So the left two carry bits are 0, 1. There's a 2's complement addition overflow. So this is mainly because when 7 is added to 3, you know in decimal number system is 10. Okay, so 10 is outside the permitted range of -8 to positive 7 in this with this given length of the number. So because of that, we can't represent this number into its complement number. It's overflow. We get the incorrect answer. And overflow may occur if two numbers are added. Uh, the two numbers added are both positive or both negative. So you can see most of the times that happens. So I thought before moving to today's lecture, it's better to do some exercises on the topic. So let me share the screen. Can you see my slides now?
Yes, madam.
Okay. Can you do these exercises? The first two exercises, I'll give you a few minutes. And I'll ask you the answers, okay? Maybe 5 minutes.
Excuse me, madam.
Yes.
අර overflow එක මුල්ම example එකේ madam -8 to +7 කියන එක ගත්තේ කොහොමද?
මොකක්ද?
අර overflow වල මුල්ම example එක.
So let me go to the slideshow, okay?
Okay, madam.
Can you tell me your question again?
මැඩම් ඒ එක්සාම්පල් එකේ මේ රේන්ජ් එක -8 to +7 කියලා ගත්තේ කොහොමද?
That's taken from this formula. So in 2's complement representation, you can represent values from negative 2 to the power n minus 1 to positive 2 to the power n minus 1 minus 1.
මැඩම් එතකොට මේ ඒකේ බිට් 4 එකක් නේ.
Yes.
එතකොට 16ක් ඉද?
2 to the power n minus 1 no?
හරි හරි.
Can you see the questions?
Yes, madam.
Okay. I think getting A pass is not very difficult if you work. You have to put time and you have to work on the examples and the exercises we discuss. I'll try to upload a tutorial so that you can do in future. In future, we have 6 weeks. I'll try to do that. And actually, it's better, I think, if I can upload a quiz because you can do it online and that's a measurement for me actually. Also, whether you have studied this section. So let me do an simple quiz, maybe 10 to 20 questions. So then you can upload you have to do it within a time. So that would help you and me both, okay? So Boolean algebra, the topic we are going to discuss is also very, not a very new topic to you. I know you all have followed physics, isn't it? So in physics also some of these concepts have been discussed. So this Boolean algebra is an algebra of mathematical logic. So why do we study this in computer science subject? Mainly because the digital circuitry in the computers is designs and behaviors analyzed with this Boolean algebra. There are logic blocks used in computer. So it's named by George Boole, who used it to study human logical reasoning. So this is a mathematics subject as well. So many of you may study that. Okay. Okay. So about Boolean algebra, the basics. So in Boolean algebra definition, we need to define a set of elements. Okay. So there are a set of elements. So there are the elements are two values 0 and 1. And there are a set of property operations. So they are the 3 basic logic operations, O and not. I think you are familiar with them, so I'm not going to very detail. And there are axioms, okay? So there are basic, there are 2 classes. There are the basic rules, which are started with, they are started without proof and the postulates. And there are rules that can be derived from the basic postulates. So those are the 2 classes of axioms. So in Boolean operations, in talking about Boolean operations, these are the basic Boolean operations and or not, basically the primary operations, and from them the derived operations NAND, NO, and so. Then there are many more. However, we discussed only this. And so this is just a revision for you. So you know, ending in between A and B, or it can be represented without the dot as well. So and of A and B, so these are 2 variables. So the 2 variables represented with 0 and 1, we can have 4 combinations. with two alternatives of variables A and B, we can have four combinations. For all four combinations, you should know the and in between those two variables. 0 and with 0 it's 0, 0 and with 1 it's again 0, 1 and with 1 only is 1. Okay, this is true only if these both of these variables are true. And okay, A and B is true only if A is true and B is true. And O operation, it's again, you can see it's represented with plus mark. It is O. If any of the one variable's value is 1, the result will be 1. If A is true or B is true, the result is true. So you can see in this combination, B is true, so the result is true. And in this combination, A is true, so the result is true. And in this combination, A and B both are true, so they both are has a positive number. So you can see that here. And in not operation, you get the not of the corresponding variable. So the not of A, when it's 0 is 1, when it's 1 is 0. So these are the basic three algebraic operations. And NAND is the AND of A dot B or A and B. And you can see when both have zeros, we get 1. And when one of them is 1, we get again 1 because AND is 0, so the opposite is 1. So you can see the 0 appears in the result and results as a result only when A and B both are true. Okay, when A and B both are true, when the AND of A and B is 1 and it's the negation is taken, so that's 0. Okay, and no is not of O, so you can see here A, O, B, it's in O, it's only 0 when both of them variable values are 0. So you get the negation of this column here. Okay, the opposite of actually OR. And in XOR, what you get is actually you get these O values apart from the values you get here. So I think it's not visible, the other part. You can see in O you get 0 and 0, 0, 1, 0 and 1, 1. So these from these combinations, 1, 1 is also 0 in XOR. So you can't see it in this table because of. So let me so that you can see. Okay. So now I think you can see the XOR operation. So those are the algebraic manipulations of Boolean operations. So the postulates which we have to believe as true. So these postulates, there are four main laws. So you can see basic postulates given here, mainly with those and in, or in, and negations. These postulates are related with them, those operations. Okay, A and B equals to B and A. Okay, A or B equals to B or A. So those are called cumulative laws. And the distributive laws, it means you can write this in expanded way also. So A and B or C is equal to A and B or A and C. So the other side is also true. If you get the or in instead of and here, it also can be expanded, distributed like this. And the identity elements, 1 O A, it means again A. 0, 0, sorry, 1 and A, it's A. 0 O A, it's A. Okay. Those are identity called identity elements. So you know when it's and with 1, the value does not change. When any variable is odd with 0, the value also does not change. So those are identity elements. And the inverse elements, you know, when you are ANDing with inverse element, you get 0. And when you are ORing with the inverse element, you get 1. Okay. So those are the basic truths which we believe. Okay. So which we can believe. So those are the postulates. And based on those postulates, we can derive some theorems like this. So when you are simplifying Boolean algebraic equations, you can use any of these theorems or postulates in your calculations. Okay, so that's why they are discussed. So from these theorems, this associative law and De Morgan's law is important. And De Morgan's law, you can see these complements. A dot B's complement is equal to A dash. This is O and this is AND. Sorry, this is AND, this is O. So in the other way around, this is O and this is AND. Okay, if they are converted and the complement is distributed. So that's De Morgan's theorem. And in associated law also, these you can see this can be interchangeably written using associated law. So those are the important things you need to remember when you are, which can be used when you are doing simplification of Boolean functions. So Boolean function is actually expressed algebraically with binary variables. So you can see here there are 3 binary variables used: x, y, and z, and there's an equal sign, and there may be parentheses used, and logical operations are also used. And when you are evaluating these Boolean expressions, you have to follow the operator precedence: parentheses first, then not, and O. Similarly, as we do in the normal additions, normal manipulations of numbers, we have to follow the operator precedence. So like that here also in logical equations or Boolean functions also, we have to follow this operator precedence. Okay. So let's look at few algebraic manipulations. So we are trying to minimize or simplify these algebraic equations. So we don't use any specific rules. We use postulates, theorems, and other valid manipulations in carrying out this. So this is equation given, Boolean function given, x plus x dash dot y. So there you can use distributive law to write in this way. And then you can use the inverse element and then identity element to write this answer in this way. So that's actually has lower number of minimum number of literals when compared with this one. So the other 2 examples are also discussed here. You can use distributive law. So when you actually convert these numbers into its simple form, you have to write down the rules you have followed. Okay, these postulates, theorems, and manipulations you have done, you have to clearly mention within brackets. And here also you inverse element because x and x dash equals 0, and then it's equal to xy using the inverse element and identity. And this one also you can do. So it's not, the answer is not given here. If there are any problems, you can ask me, okay? And I will give you how you can do it. So, so we do first. We discussed today about the main what is algebra, and then the algebraic operations, and then what are the postulates and theorems available in algebra, Boolean algebra, and then how we can simplify a Boolean function using those algebraic postulates and theorems. And we manipulated, we simplified some of the functions using those theorems and postulates. And now we are going to talk about the complement of a function, how we can convert a Boolean function into its complement. So here, De Morgan's theorem is really important. So this is the general form of De Morgan's theorem. It's better if you can write down this and try to understand, realize what is really happening here. So you know A is OBOC. So its complement is equal to complement of each and every element O's. Okay, you get O instead of and here. So you have here what? Or in. Here you have ends. Okay. And to the whole expression, you have the complement, and here for each and every element you have the complement. Okay, so that's actually the speciality in the De Morgan's theorem. So there are, I mean, proofs of De Morgan's theorem in mathematics. If you want, you can refer how this becomes true and why this is true. There are very nice proofs of this De Morgan's theorem. So when you are complementing a function, you can do it by applying De Morgan's theorem. Okay. So what you do is you can find the complement by taking their duals and complementing each literal. So what you can do here is there are two main ways. You can either apply De Morgan's theorem or take the dual and complement each literal. So, so those are the two main ways you can find the complement of a function. Okay. So either you can follow De Morgan's theorem, or you can take the duals and complement each other. So these are the two main ways, this one and this one. Okay. So, so this is not actually cutting the. Okay. So, okay. So these are the two main ways. So let's look at the first one. So assume that this is the this is what so this is the function given to you. So what would happen if assume this function as a, the complement's complement, it equals to a. We get the complement and then get the complement. Okay, it's equal to a. So this is actually applied here in De Morgan's theorem. So to apply the De Morgan's theorem, we need to have some complement. So we make this into a complement in this way. We try to start from here and then put a complement to apply De Morgan's theorem. Okay. A equals its complement's complement. So this F1 equals this function's complement's complement. So this did not come, I mean, the same, I mean, according to this, we can write this. Okay. So then then we can apply De Morgan's theorem. So that's what they have done here. Okay. So these are the two components in this equation, and then you can get the complement of these two numbers. And then you can convert that using the De Morgan's theorem. There are two major theorems you can use, like this one or this one. So corresponding can be applied and then converted into its corresponding form. So either that way on the or the other way around, you can take the dual. So what's the dual? So when you are taking the dual, what you do is actually you take the opposite of these opposites. No, it's not opposites in one way. If you have the O sign here, you write the AND sign in the dual. Okay, and if you have the AND sign in the original equation, you write O sign in that dual. Okay, so you can see here x dash and y dash, sorry, y and z dash. Okay, so that's one term in this equation. So that is converted into this dual by, if you find AND sign, it's converted into plus sign. If you find AND sign again here, you convert into plus sign. Okay, and you get plus of that whole term, and then convert that plus sign into dot. So that's how you can take that it's dual, and then you can complement each literal to convert it into corresponding complement of that corresponding F1. Okay, so that's how you can do that. So that's about two things we discussed: algebraic manipulations, simplifications, and complements. And now we are going to talk about something also familiar to you, which is truth tables. In truth tables, we are trying to do a verification. So it shows you the relationship between a function and its binary variables. So truth table, it's something like this. I think it's not very new to you. It's familiar to you because in secondary level also you have discussed about truth tables. In truth table, we try to write every possible combination of inputs. Okay. As an example here, there are two inputs. So how many possible input combinations are there? There are 4 possible input combinations with 2 variables, A and B, with 2 values for each variable, 0 and 1. Okay. So we can actually use truth tables for verifications of postulates, theorems, and for some, we can get the output of a certain given algebraic equation. And here also, you have to follow the operator precedence when you are evaluating your Boolean expression. So as an example, you can consider the truth table of Morgan's theorem, the Morgan's theorem. Okay. So A dot B dash equals to A dash plus B dash. So that you can take the values of A and B and then get a column for A dot B dash and a column for A dash plus B dash. So then you will get at the end the same results. Showing you that the left hand side equals to the right hand side. So that's one way of proving some Boolean algebraic equations. So that's about truth tables. you have to use truth tables when you are trying to show the when you are trying to prove that some algebraic equation is true or not. And then about max terms and min terms. So why are we talking about max terms and min terms? Because for some equations, when you are asked to minimize some algebraic functions, some function, it's really difficult to use those algebraic postulates and theorems and minimize. Okay, so we are going to discuss further about the different methods available to minimize these algebraic functions. To study about those functions, we need these basic terms and their definitions. What are they? We need to remember them to apply them to those applications. So that's why we are discussing about min terms and max terms. So min term is defined as and of n variables, with each variable being primed if the corresponding bit of the binary number is 0 and unprimed if it's 1. Okay. As an example, min term of x and y with the values 0 and 0 is x dash y dash. Min term is and term. You can see we have get the and of x and y. However, if you have the binary number 0, then you have to get the prime, and it should be unprimed. It's 1. If it's 1, you can look at the second row. Okay, so y has the value 1, x has the value 0. So when x is primed, y is not primed, mainly because we have not taken the dash. It means not prime when the value is 1. Okay, so you can see 1 and 1, they know both are not primed. Okay, x and y. And term is taken in min terms, and in max terms O term is taken. Okay, and the opposite of this priming thing. Prime mean we are getting the complement. So here 0, x value is 0 and y value is 0. So the max term comes with O, or in x and x O y. Okay. However, x is not, dash is not taken, mainly because the value is 0. Here dash is taken, the value is 0. Okay, so the opposite. Min term and max terms are opposites in one way. If you have x, you have to write x dash in the min term. If you have x, if the value is 0, you have to write x. So here we wrote x dash when 0. Here we wrote x when it's 0. Min terms and max terms are opposites of each other in every way. Okay, from the sign and the complement also. So so this designation which capital O simple M are used to denote these min terms and max terms. So so that's about min terms and max terms. So keep them in your mind, and we'll be using them in future. Okay. So Boolean functions, we can evaluate Boolean functions using truth tables. So you can see here, we are given with the function f1, and how many, so when you are asked to evaluate a Boolean function by truth table, you have to see first how many variables are there. Okay. So there are 3 variables, x, y, and z, and function f1. So you can see you have to write all the combinations with 3 numbers, so 3 variables. So how many combinations are there? 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. So there's a pattern you can write. 4 zeros, 4 ones, 2 zeros, 2 ones, 1 0, 1 0, 1, like that. Okay, it's easier if you want to write it quickly. So that's the truth tables, all the combinations of with three variables, and look at the F1 value. Okay. So you have to here we have to consider min term for each combination of the variable, which will produce A1 in the function. Okay. So F1. So you can take all of these terms, x dash, y dash, z, x, y dash, z dash, x, y, z. So you have to take each and every term, x dash, y dash, z, and you have to write the corresponding value here. So any Boolean function we can express it as a sum of min terms like this. And F2 also you can write. So when you have x, y, z here, it is 0, and x dash, y dash is z here, and it's not actually marked here. So it would produce 1. So this corresponds to x dash, y dash, z correspond to this row. If you see this one, you can consider that x dash, y dash is x0, y0, you know, in min terms. So you have to find the values for these min terms, x dash, y dash, z, which is 1, and x, y dash, z dash, x is 1, y dash, z dash, it's 1, and x, y, z, x, y, z, 1. So that's how you can represent a Boolean function in this using a truth table like this. Okay. And you can write it using max terms. So any Boolean function can be expressed as a product of max terms. So they are, instead of 1, we use 0. Okay. X plus y plus z, we use 0 here. Okay. So that also you can see from here. X is 0, y is 0. The term we are represent is x plus y. Okay. So we are doing the opposite now. We are given the term and we are trying to represent that in the truth table. So x plus y plus z, which is represented by a 0. Why do we represent it by a 0 rather than 1? Why do you do that? Because in max term definition, also it says that we are going to represent those values 0th with not primed numbers. Okay. So that's how we can represent a Boolean function by a truth table with either min terms or with max terms. So you can see M0, M1, M2, M3, M4, M5, M6. So the other one actually also can be represented. So you can consider this truth table, and now you can express the function either using min terms or max terms. Okay. So it's given here. You can write either using min terms or max terms. So when you are using these min terms, so you have to consider ones here. Okay. When you are considering max terms, you have to consider zeros in each and every column. So so let's get one of these values and try to explain. So this is written with what? Min terms. Okay. When you are writing with min terms, you have to get the end of each and every variable. Primed if you see 0, and unprimed if you see 1. So you can see here we have zeros. Okay. So each and every variable need to be primed, because in this position 1, we have all the variable values 0. So we get the priming of x dash, y dash, z dash, or the complement of x and y and z if we see zeros in your mean term. Okay. So in the second one also you have 1. So again, so this is a mean term. You have to write this as a mean term in the expression. So it's x dash, y dash, z, y. Because x and y values are 0. So we get the complement of them. And z is 1, so we are not taking the complement. Okay. And plus x dash, y z dash. From where does it come from? Again, from the other one value in f. Okay. X dash mainly because x is 0, y because y is not 0, and z dash and z is 0. So that's the third mean term we consider. And the fourth mean term is coming from this row. There you have x1, y0, so you get the prime or the complement of y, and the z is equal to 1. Okay. So using this truth table, you can write F3 as a origin of minterms. Okay. So if you are given any truth table with some function and with some variables, and if you are asked to write the function, okay, there are two ways you can write. This is one way you can write using min terms, and the second way is using max terms. Those are the two basic ways you can do this. Okay. So again, listen. What you ask here is using the truth table, write the function of the Boolean expression represented by this truth table. Okay. Write the Boolean function represented by this truth table is the question. So to answer that question, there are two main procedures you can follow. Either you can write the answer with min terms, or you can write the answer with max terms. So what's a min term? What's a min term? So min term is defined here. Min term is defined as n term of n variables, with each variable being primed if the corresponding bit is 0 and unprimed if it's 1. Okay. So you can see x and y have zeros here. Okay. So they are being primed mainly because the corresponding bit of the binary number is 0. These are 0, so these are being primed and get the n term. Okay. This is not primed because the value is 1. So when we are finding the function by using a truth table, what you are given, so this is one function given, this is another function given. Okay. So just forget about function f2 for the moment and just concentrate on function f1. Okay. In function f1, you have 0 here. Okay. So when you are writing the min terms, so what you have to consider is ones, not zeros. Okay. Consider a min term for each combination of variables which produce 1 in the function. So in the first way of answering this question is writing the function as a set of min terms. So when you are writing the function as a set of min terms, you have to consider ones in F1 field. How many ones are there? There are 3 ones in the F1 field. So as F1, you have to consider all these terms when you are writing F1. Okay. F1 equals to the addition or the or in of these three terms. So that's what is being done here. Okay, M1 plus M2 plus M3. Sorry, M7. M1 plus M4 plus M7. Okay. M1, M4, M7. So that's it. This correspond to M1, correspond to M4, M7. These are the min terms. Min term is the n term of n variables, with each variable being primed if the corresponding bit is 0 and unprimed bit if it's 1. So here, these are 0, so you prime those two variables, and z is 1 and you don't prime that variable. And so here we have O sign, because we have to write OR of the min terms as the function at the end. And here we have x, because the value is 1. Other two are get the prime because they are 0. And in the other term in 7, you have all the values 1, so you are not going to prime any. Okay? So similarly, there's an exercise for you. You have to consider f2 and write down the corresponding function using min terms. Okay. So here you have how many variables? So how many corresponding min terms you have to write? 1, 2, 3, 4. When you're writing the function with min terms, you have to consider ones. Okay, they say it here. 1 in the function. Function is 1 only when 0, 0, 1, 1, 1, 0, 0, and 1, 1, 1. At those 4 positions only, you get 1 value. Okay. So then you have to write the corresponding min terms here in this space provided. You can do it at home. And when you're the other way around, when you're writing the Boolean function, using max terms is the second way I told you you can do this. Okay. So when you're writing max terms in the F1 field, you have to consider zeros rather than ones. Okay. Previously we considered ones. Now we are considering zeros in max terms. In max terms, we use zeros in the function field, and in min terms, we use ones in the function field. Okay, that's the basic difference. And we have to take the end of all those terms, all the max terms. So now remember, in max terms, what we are doing is we get the O term of variables, and if the corresponding bit number is 0, we get the unprimed variable, and if it's 1, we prime it. The opposite what we did here. Okay. If you find 0 in the variables, we get the variables as unprimed. If you have 1, we prime it. Okay. So here, similarly, so for each and every corresponding, when you are asked to write the terms corresponding to these values. So we have x, y, and z. The values are zeros. Are you going to prime or unprime? It would be kept unprimed. Okay. X, y, z, and we use O term instead of O sign instead of n sign. That's a max term. So you can see here in max terms we get what? OR. So we get the OR of x, O, y, O, z, because all of them are zeros. So, so that's the first term. And the second term corresponds to this value here. x is 0, y is not 0, and z is 0. And so we have x, we get x o y dash o z because y is only 1. So likewise, let's go to the third 0 we get in the function. So this term needs to also be written. Then we have x plus y dash plus z dash. Okay. And in the fourth term, we get x dash plus y plus z dash. And in next term, we get x dash plus y dash plus z. Okay. So that's how we can write the function in terms of max terms. So this function we have written using max terms. Okay. It's this function is written by max terms here. And as an exercise, this function f2 you have to write using max terms in this given space. So when you are given a truth table, so we don't know how this value f3 came here, okay? So you don't have to worry about that. So you are given 3 variables and the output. 3 variables and the output. There are 2 outputs given, f1 and f2, don't confuse. When you write in one, this forget the other one. When you write in this function, forget the other one. When you write in this function, f2 is not related with f1, they are independent functions written with x and y and z. You are given only the end product. Okay, so you have to write whatever the combination of x, y, z can produce this kind of f1. Okay, so that's what you have done here. So there's an exercise. So you are given some output for some variables. So you have to express the Boolean function of this f3. So what you can do is you can follow 2 methods. Either you can write the function using max terms or min terms. That's what it's been done here. In the function f3 in the first row, what they have done is they have written the answer using min terms. Okay. And in function f3 in the next row, it is written with max terms. When you are writing with max terms, what are you considering? You are considering zeros instead of ones in the in here. You have considered zeros. So there are 4 terms and there are 4 terms. Okay. In the first term, you have 0, 1, 1. So 0 is there. So you are getting x. And 1 is in the next variable. So you are getting x dash, sorry, y dash. Then 1 is in the z column and again z dash. So this is the corresponding max term for the 0 here. And corresponding max term for the 0 here, the first one is 1. Sorry, I think this is not written in order. So this is corresponding to the last one, 1, 1, 1. Yes, there are some dash missing here. Okay, you have to correct that x dash plus y plus z, and here x dash y dash z for this one, and for this one x dash y dash z dash. This need to be corrected. The second term need to be corrected. Okay, it be x dash. Okay, so like that you can write any given Boolean function in a truth table. We don't know from where it came. Okay. So we don't know actually from where this final value came. However, what you have to do in the question is to write down an equation so that we can get this using the input values, input variables x and y and z. So we use x and y and z, and there are two major ways we can do this, either using min terms or max terms. With using min terms, you have to write the function looking at one values in the corresponding column, and using max terms you have to write the function using zero terms, okay, in the corresponding result field. So this is the result field or the function field. Okay, now I think it's clear for you. So in this lecture we have discussed mainly about Boolean algebra postulates, theorems, and using them how you can simplify a function and how to get a complement of a function. So that's the second thing we did. And the third thing is this one. How can you write down the corresponding function if you are given the truth table of that function? Okay. That's the thing we did. So in writing the function, there are two major ways you can do it. The first one is you can write the equation with min terms, and the second one is you can write the equation with max terms. Okay. So in this window, a function is written with min terms, and in this window the function is written with max terms. So the example is given for f1 only, and it's up to you to write the function of f2. And function of f2 here also you can write with max terms here. So there are two independent functions given here, okay, for the same input variables. So don't confuse. So here what we did was we use a truth table to show the results of a corresponding function. So what we are doing here is not similar. Okay, so that is similar to, that is familiar. This one is familiar to you, I know, because in secondary school also you did this. You are given a function and you are asked to use a truth table to show that this is true. Okay, or you are given a function in this side and you are asked to write a function, you are asked to draw the truth table of that function. So that you have done. But what we are doing here is something different. Okay, you are given the truth table, variable values, and of the function and also the function values. Okay, so what you are asked to do is actually now write the corresponding f1 using xyz terms. We don't know how did f1 became 1. We don't know. Okay, it's given in the question. So for this input combination, it is 1. So it's something like this. Let me explain using a practical example. Okay, assume that there are 3 processes. Okay, assume that this is a tire manufacturing company. Okay, this is process A, process X, I will do X. Okay, this is process Y. And this is process Z. Okay, so these are the 3 main processes you have in a company. This is a tire manufacturing company. Okay, so depending on this completion of these processes, the manager decides whether the tire is okay or not. Okay. So the process X is carried out to the tire. Okay. And okay, so the decision of whether you are whether the manager decides to this is manager's decision. Okay, this is manager's decision. It's one, so it can be one. The one can represent manager decides to sell the tire, or if it's not, it does not pass the quality test. So these are the three quality tests: X, Y, and Z. It depends on the manager. Okay, we don't know whether sometimes he may pass it, sometimes he may not pass it. So for this X, Y, Z, you may have values 0 and 1. If X quality test is passed, it would have value 1. If the Y quality test is passed, if you would have 1 here. Like that. Okay. This can have either 1 or 0. And this also can have either 1 or 0. And this also can have 1 or 0. Okay. And depending on this 1 or 0 value, the manager would decide either it's 1 or 0. 1 represent passed and 0 represent fail. Fail means you are not going to out the tire. It does not satisfy the quality requirements. 1 pass, 0 not pass. Okay. Either he would pass the tire or not pass the tire. So this is actually, this can be, I mean, if you look at the manager's decision, you can formulate a table like that for this problem. So this is in this tire company, there are three quality tests, X and Y and Z. X would have either 1 or 0, Y would have either 1 or 0, and Z would have either 1 or 0. Okay. So you can write this in a truth table, this decision. Sometimes the manager passes tires when this is 1, 1 and 0. Sometimes he passes tires 1, 0 and 1. So like that, we don't know the reasoning behind manager's decision. So, so if you are asked to write the reasoning behind manager's decision, you can write a truth table like this. Okay? Like this actually. You can have it's quite difficult to draw things here. You know. I'll draw it in simple way. You can have manager's decision. I will mark as D. Okay. X, Y, Z and D. X, Y, Z and D. So X can have 1 or 0, Y can have 1 or 0, Z can have 1 or 0. So how many combinations can I write? 0, 0, 0, 0, 0, 1, like that. 0, 1, 0. Like that, you can write the combinations and then look at manager's decision and put 0 or 1. At the end, you know his mechanism. Okay. So you are given a table like this in the question. You don't know from the hell you get this. Okay. But what you are doing is actually you are trying to figure out from where, from which combinations of X, Y, Z is formed. That's what you are doing. Okay. So you get each and every combination and try to come up with a solution. So there are two major ways you can do this. You can consider ones in the D field, in the function field. So this is the function actually. There are input combination and we don't know how these functions came up. You can either use min terms or you can use max terms. If you are using min terms, you have to consider ones. If you are considering max terms, you have to consider zeros. All the rows considering zeros. Okay. And then write the equation. And that would represent manager's decision behind, decisions equation. Corresponding to manager decisions. Reasoning behind that. Okay. So that's what we did here. Is it clear? Is it clear for you? Now? So I'm going to finish the lecture now. So if there are any unclear places like your friend previously asked, you can ask me now. So what we basically discussed was this today. We discussed how for a given algebraic function, how you can find a simplified function. Okay. And then secondly, we discussed about how to get the complement. And thirdly, we discussed about how we can represent a function using function given in a truth table using max terms and min terms. Okay. So if you can do this example at the end, that's it for that part. Okay. You should express the Boolean function in these two terms. And if you look at the past papers, you will see you are asked to develop a truth table for a given scenario. That's what actually we discussed in whiteboard. Okay. So you will be given a scenario like this. You will be told a story. And then from this story, you have to develop a truth table. And then you have to develop the function to describe the reasoning behind. Using max term or min term. Okay. So that's the basic logic. So you have to understand the logic and from the given scenario. So you have to write the corresponding table and derive the functions for a real-time scenario. So that's that can be seen in the past papers. You can try to develop the table and try to write out the functions. After that, you are you have studied now. Okay. You can, I think, answer 1.5 questions. 1.5 questions now. We have covered syllabus up to that. Okay. I think you all may be able to understand. So if you have not understand, you have to discuss with your friends and refer the books and refer the internet and ask me if you have further any questions. You can do the past papers and if there are any problems, you can let me know. Yes, I will upload the note to LMS and also the video recording to the LMS or to my Google Drive, actually YouTube channel. The mainly reasoning behind is sometimes I don't know whether I will be able to upload this if it increases certain capacity. I can't. Okay, so let's see. I will do both or either one and put it in the LMS. I think some of you that did have connection problems, you went out and come in and asked me to enter the lecture. Okay. So because of that reason, I'll be uploading the video recording of this lecture. Okay, is there any problems? I mean, without talking, we can't do this. You just listen, and I don't know whether you listen here. I mean, why can't you turn on your microphone and say yes? Okay, so I'll end the lecture for now. Let's meet next week.